Good afternoon, Ravi sir.
Yeah, hello, can you hear me?
Yes, sir. I can hear you now.
Yeah, fine. Yeah, that's what I'm just about to send you a mail. I won't send the mail now. So now it's working, right? I mean, it works on my mobile, but only thing is, my laptop can work, that doesn't matter. But you can hear me, right?
Yes, sir. I can hear you.
Yeah, good.
Hope you got my mail regarding
Yeah. Yeah, right. Yeah. I mean, yeah, of course, I got your mail. Only thing is, on my laptop, I could not log in because there is some issues, in fact. I can hear, but then I cannot speak. I don't know why. Anyway, that doesn't matter. I think this is good enough.
Okay, sir. Good afternoon, CNC sir.
Good afternoon.
I'm just seeing your typing random names
Yeah.
because it's hard to find this.
CNC, where is Pati today?
No idea.
Yes, when with Anu madam, I think Pati sir went to JIT college.
Was he for what program?
I don't know in detail, sir, but he told he's not available today.
I know that. So, okay. This is actually based on the RSW conducted by us. They have actually conducted an RSW in their campus. This is JPR Institute of Technology.
Oh, I see.
So a lot of colleges are doing that. See, they are trying to adopt. They're just taking the same template and they're using it. And I think they've invited a PALS team as judges or some, whatever.
Oh, I see. Very interesting.
Good afternoon, Chandar sir.
Good afternoon. Hi.
Good afternoon,
Good afternoon,
Chandra.
Yeah. Good evening, Chandar. My name is Ravi Venkatraman.
Good evening, sir.
From 71 batch of IITM. I'm sure you are not born in 71, right?
No,
Yes.
even his grandfather wouldn't have been born, Ravi.
So welcome to the session. We all are waiting eagerly for your session. I heard so much about you. So, we're all waiting for the session.
Nice.
Let us wait till 1:30.
Yeah.
And then we'll start. You are based in Bangalore, is it?
Yes.
And you are from IIT KGP, right?
Yes, yeah.
Which year?
So 2012 to 2017. I was a dual degree.
I know. I saw that.
Yeah.
Anybody? I don't think I know anybody from this. Anybody went to, TCS or some other companies?
No, I don't think so.
Oh, only for IBM, is it?
No, I mean, I don't remember. I don't remember anyone, but yeah.
Yeah, many would have gone to TCS from KGP, right? Right. And
See, Chandar,
Chandrasekhar.
it is better to keep in touch, with your own classmates. You don't know when that will help.
Yeah, sure. Yes, I agree.
Right? Because, at some point in time, you find that networking is more important.
Yeah.
Than something technical, right?
Yeah.
So you need to keep on maintaining all your network. One could be from the school, one from the college, one could be from regular employees if you worked anywhere else. So you have different networks, or you can also join, things like NASCOM or maybe TIE or maybe MMA, of course, in Chennai, in fact, so on and so forth. Because today youngsters don't have even time for networking. Because they're always busy on their WhatsApp and other apps, which is unfortunate.
Yeah.
So, where is your office in Bangalore?
Sujata here.
Hi, Sujata.
Good afternoon, Ravi. Good afternoon, CNC.
So, Sujata, you're in Pune, right?
Yes.
Okay.
hello, Chandar sir. Can we have a screen sharing check?
Yes. I was going to ask.
Please do the check. I think audio video seems fine now.
Yes.
So, Sujata, you said I first play the video, right?
Yeah. I'll start the session and hand it over to you, Ravi.
Oh, sure. No problem at all. No problem.
So my screen is visible. I can even start the slideshow.
Yeah, it's visible.
Okay. Yeah.
Students normally take some 5-10 minutes to warm up and join the session. So we will use that first 5 minutes to play a small video wherein one of the student who attended the earlier sessions, she's unable to attend today. So she said she will watch the recording of today's session. But she said she has sent a video recording of recap on the session one, actually, what happened in session one. So she was enthusiastic about sharing the video. So I told her, okay, no problem, we'll play it here. So
that's good. Yeah.
So we'll wait for 1:30 and then we'll get started.
Sure. Yeah.
Yep. How many people have joined so far?
136.
Why, that's a good number, right? I'm 125. We have 5 more minutes to go. So it's like a T20 match, right?
Yeah.
We have 5 more minutes. Last 2 sessions, we have been having 1,000.
1,000.
We'll have people coming in late.
I know. But let us not wait for them. We'll start at 1:30.
Ravi, you were talking about MMA. Are you going for a session today in MMA?
I am planning to anyway, right? Because exactly. Meanwhile, I just got held up on this. But I'm planning to. I wanted to meet that Kumar, because I had been there to the factory also. And Kumar has also joined as a member of the IIT Alumni Center.
Right.
So I just thought I'll try to go down there, say hello to him.
Yeah. Yes, Sesh's nephew is doing book launch.
Sorry?
Seshadri's nephew is doing book launch today on artificial intelligence.
Oh, is it at MMA, is it?
Yeah, I thought you were referring to that.
No.
Oh, you don't know about it?
No, he was saying something today. Correct. He was saying something in MMA.
Yeah, he written a book on AI.
Yeah, I don't know. You see, I am attending a lecture on AA for Aam Aadmi. They're being organized by, Mahalingam, because it is through that Palkiwala Foundation.
Okay.
And the speaker is very interestingly a guy called Nitin Paranjape. I don't know whether you heard about him.
Yeah, I've heard about him. Yeah.
He is the global CEO of Unilever.
Yeah.
He's hardcore marketing guy. So he's going to talk about AI for Aam Aadmi. This is going to be held on Saturday evening at 6:30 p.m. at the Music Academy. So since I got the invite from Mahalingam, I want to attend it, show my face, mark my attendance.
No, I can't attend this book launch because I'm in Bangalore today.
Oh, you are in Bangalore, was it? How long are you going to be there?
This week till this weekend. So Monday I'll be back.
Monday you're back. I'm going to Bangalore on Monday evening.
Okay.
Now Chennai, Bangalore have become really like one city, right? It's like a suburb only.
Correct.
Takes hardly 4 hours. The Vande Bharatam was really, I think, great revolution.
Right, yeah.
Now you have 1 in the morning, 1 in the evening, and that makes it all the more better. Now for Hyderabad, you don't have this kind of train. I want to go to Hyderabad in the first week of March. Thought I'll try train. Train takes anywhere between 12 to 15 hours or 16 hours. And I didn't know Hyderabad has also got now, in fact, 3 stations.
Yeah, correct.
I believe one station is almost about 30 kilometers from Hyderabad. And the train to the station is easily available. Fortunately, I didn't buy that. That 30 kilometers you have to travel into the city. More like airport.
A lot of people have joined with 1611219 as the Zoom name.
MAMSET and JIT students, DGCT students are attending in classrooms.
Oh, okay. Okay, I'll mute myself for now. Okay.
I think Kishore, we should get started with the video because that will take some 3-4 minutes. Meanwhile, the students can also join.
Okay, I'll start the recording, madam.
Yeah, you should. Mr. Chandar, is it okay with you?
Yes, yes. All good.
Ravi, are you fine? Should I get started?
Oh, yes, absolutely.
Yeah. So, Kishore, please start the recording. Good afternoon, all. A very warm welcome to all of you for the third session in the Industry Assisted Lecture Series by IBM Research. So, warm welcome to Mr. Chandar Govindarajan, a research scientist from IBM Research Labs. I also take this opportunity to welcome faculty and students from the PALS partner colleges and to all the PALS champions who are attending the session today. Just a quick recap, we have completed 2 sessions already, rather 3 sessions. The day one had 2 topics covered. We covered topics PyTorch basics, PyTorch compile, and inference systems. I hope all of you would have either attended the session or must have watched the earlier recording and also marked your attendance because all the marking the attendance will only count for the certificates. Well, when we have the student, Miss Reboth from Arunachala College of Engineering for Women. She is pursuing her BTech third year from Nagarkoil. She picked up this opportunity. I've been, I'm constantly putting a message in the WhatsApp group asking for volunteers to recap either of the sessions. So when I gave this opportunity to all of you, she was bright enough to use this opportunity. So she has given us the video. She has volunteered to give a recap of the session 1. Now, of course, due to some commitment at her college, she was unable to join the session today live, but was bright enough to send a video recording of the recap. So what I would do now is I will quickly like to play the video. I hope all students here will, resonate with her, sit with her and understand what has gone through in the last sessions. But I would also like you to take a cue from her and try and use the opportunities that are being created for you. So that is the message that I would like to say. But before I play the video, a quick recap on the rules that we will like to follow during the session. Just give me a second. Chandar, if you can stop your video sharing for a second. Yeah. So we will not be allowing you to unmute at any point in time, neither chat. The chatting can be possible only to the host and co-host. But however, that doesn't stop you from asking questions. We keep encouraging you. Kishore will be posting the mail ID askpalspmo@gmail.com. You can write to that email. We are monitoring this email through the session, point 1. Or you can chat with the host and co-host. Put only relevant messages related to the question. At any point in time, whenever we get the opportunity, we will definitely, ask this to the speaker and get your questions answered. If at all there are any quick questions, use the raise hand option. But if you are constantly raising your hand unnecessarily, we will definitely not know which is an authentic ask or which is not a authentic ask. So please make sure that you raise your hand only when it is needed. Attendance link will be posted in the chat box, both here in the Zoom chat and in the live chat in the YouTube streaming. Please make sure to mark your attendance. Use only the registration ID email that you have used during the registration. Use that email ID to register, mark your attendance. And we will also have a quiz at any time during the session. So please ensure that you are connected with us. Slido link will also be pasted in the beginning. Please join the Slido quiz and be ready for the quiz. Feedback link, recording and other materials will be shared by mail later post the session. And I just would like to also mention that we'll be having a final quiz very soon. Details on the final quiz will be shared by Kishore post this session. For sharing, attending taking the final quiz is mandatory. That is one more step mandatory to get your certificates. So with that, I would like to play the recording. I'm stopping the share and I will start it again. 1 second. Just give me a second. Kishore, can you confirm if my screen, the video is shown?
Madam.
Huh?
Yes, I can see the video. You can play.
I'm playing. I hope the audio will also be played.
Yes.
Hello everyone.
Yes, that is.
I am going to summarize the session 1 and session 2. First of all, we are going to see session 1. On session 1, we first saw gen models, which is also called as generative models, and also language models, which is helps in text generation, translation, etc. Next, we saw about how to build LLM models. First, we collect the data, then pre-process it, then train the model, next fine tune it and evaluate it, and finally deploy it. Above processes, we give training and fine tuning to the model, and next we saw about inference architecture is when application give HTTP request to the inference server, and these requests are sent through HTTP through the scheduler. This scheduler will send this request to the inference engine, in which we will be batching the requests and give it to the model. The model will give the response and also send us a HTTP response back to the application. Next, we came across PyTorch, which is a library in Python, and it creates dynamic computational graph when doing operations, which is represented as a graphs. Next, we saw about tensors, which can convert anything into something that can be understood by the model, which is in the form of multi-dimensional array. According to the dimensions of the inputs given to the model, it will store in the arrays sizes ranges from rank 0 to rank 5. And it also divides the text inputs in the dimensions of batch size, sequence length, and embedding size. And we saw the tensor with relation to the storage, in which the storage stores the physical data like data type, size, etc. But in tensor, it shows the logical view to the user, in which if we ask 2 by 3 matrix into changed into 3 by 2 matrix, the shape will change, but the contents will not change. But if the contents in the 2 by 3 matrix are changed, then it will form a new tensor. Then we saw about transformers, which brought large language model wave. Transformer is a type of logic or a mathematical thing that happens in the model, which transform how the data are viewed or understood. When we giving an input to the model as a sentence, it will convert into tokens, which is understood by the model. And this action is done by tokenizer. Then we saw about attention, which is a layer in the transformer representation of the model. This attention concept will give more sense to the input that we give. When we give input to the model, it will convert each word into tensor object. This is called as embedding, which are done by tokenizers, and these embeddings are plotted in the vector space, represent different values in the tensor. Okay, when we train the models, the workload is very high because the model consumes a lot of resources, and it's a time-taking process to train and fine-tune models. So we need to see how it performs, and we also need to consider performance issues. We need to monitor the overall performance. This is done by PyTorch profiling. This is done by PyTorch Profiler, which is an inbuilt tool in PyTorch. This PyTorch Profiler will give the profile when running the code. This PyTorch Profiler is also very simple and very flexible. It shows how much memory is used. This also shows what are the operations are done in the code, and it also shows what are the functions called. Then we saw about eager graph-based ML frameworks. PyTorch, in PyTorch, by default, it will runs models in eager mode because it is the codes are dynamically executed by line, and the prototype, it is also very flexible, and the computational graph of code is created at runtime when each code of line is running, and but it is bad performance for production. But the graph mode is used in TensorFlow. When the torch compiler runs, three steps are running behind it under the hood. There are three steps. They are graph acquisition, graph lowering, graph compilation. And then we saw about Torch Dynamo, which is a compiler, a just-in-time compiler, and we saw about its functions like GOTS, graph breaks, and we also saw about AOT autograde, which captures both forward and backward computations as if its graphs are ahead of time. And then we saw about Torch Inductor, which is a backend compiler for Torch Dynamo.
So that's all we had from the student. So I appreciate her to have taken this effort and put all her learnings into one video and sent. I appreciate you, Rebath. So with this, I would like to now introduce our speaker for the day, Mr. Chandar Govindarajan. For that, I would like to invite Mr. Ravi Venkatraman, PALS champion, to please do the speaker introduction and also tell us about the topic for the day. Over to you, Ravi.
Yeah, thank you, Sujata. Can you hear me?
Yes, you can. Yes, I can.
Oh, yeah, thank you. Welcome. Well, dear PAL students from 70 different colleges from all over South India, as well as the faculty members from various colleges, I'd like to extend a warm welcome to you all, along with Mr. Chandar Govindarajan, for this exciting session on distribution system. Chandar is a research scientist working for IBM Research. She is the world's largest technology company even today. Many of you may know that the life of technology company is not more than 15 to 20 years. I can quote so many examples. Like for Yahoo. Yahoo was the world's largest company in terms of market cap one day. And where is Yahoo now? It is dead and buried. Where is Digital Equipment Corporation? It used to have very, very fine operating systems and RDMS. It's gone. Wang Computer, who invented word processing. I don't know how many of you will have seen Wang Computer. I used to work with that. And that's also gone. So average life is around 15, 20 years. The only exception is IBM, which keeps on transforming itself. Right? And then it is able to, become more flexible, agile. So now IBM now has gone through so many transformations. When I joined, service in TCS way back in 73, IBM was a pure hardware company. Then they slowly started getting into software and getting into RDBMS and getting into OS and so on and so forth. So today IBM is basically a technology solution provider. And it is indeed very lucky that we have got somebody today from IBM Research. Chandar is a research scientist from IBM with 8 years of experience. He has had previously worked in multi-cloud, observability, blockchain. His current focus is on systems for LLMs, which is obviously large language models, and which is a very, very hot topic today. He completed his dual degree in computer sciences engineering from IIT Kharagpur, which is the oldest and largest IIT of all the IIT family. So I like to extend a warm welcome again to Mr. Chandar. He is based out of Bangalore IBM Research Center. The topic today is supposed to be distributed training. Let me give you some basics about this also, and then wind up. I don't want to take much of your time. Training deep learning models is highly resource intensive. This talk will explore how the training process can be distributed across multiple GPUs to improve the efficiency and scalability. We will also summarize the key parallelization strategies, including data parallelism and pipeline parallelism, and discuss how PyTorch supports these approaches. We will also look at the communication collective the PyTorch provides to enable fast and efficient multi-GPU and communication. I request all the people to listen to the talk very carefully, because there are going to be quizzes in between or maybe at the end. You guys have to complete the quiz if you want to get a certificate. So, please and keep your eyes and ears over the thing. And over to you, Mr. Chandar Govindarajan now.
Thank you, sir. Let me share my screen. Okay, so is my screen visible?
Yes, it is.
And it's in presentation mode, right?
Yes, it is.
Okay. So thank you for the warm welcome. So let's get started. So today we'll be talking about distributed LLM training, right? But I'll give you context around training and other things also. So it'll be a broader topic. Okay. So this is an example. You see here picture of a typical transformer architecture, right? So you would have used different LLMs like OpenAI's ChatGPT or Google Gemini, but at the end of the day, the core architecture of all these models are very similar because they are based on transformer architecture. It looks somewhat like this. There are various blocks, and of course, there is more complexity, and each block is there for a reason, and so on. But for now, you can imagine that there are matrix multiplication operations. Okay. And so you have this kind of model, and you have some layers, and they have different responsibilities. So normally the simplest thing you can do with this kind of model is a forward pass. Okay, so you have seen this in the previous talks also, but I'm just giving a recap. So there is a model dot forward of an input, and it is shown in the summary also. Your input is usually text, which you tokenize and then convert into a floating point number, and then you pass it through this system. So what will happen is each block will operate on the input, and it will provide an output, and it will keep going through the structure, through this architecture. And again, you finally do something with the number, right? That's the way a single forward pass works. So now I'm going one step ahead, right? So forward pass is one token going through the system once. But when you interact with the ChatGPT or any other LLM, you actually get text. You get multiple tokens. You ask a question, and you get multiple tokens back. So what there actually is happening is there is a loop. So the same forward model dot forward is actually happening in a loop where we pass some n tokens. We try to take one output out, one next token, and that is like the next word you can think. And then we again do the same thing. So there is a loop, and that's what is the forward pass, like a continuous set of forward passes. So that is what is known as inference. So that is what happens when you use a LLM. But somebody has to train the LLM, right? So these companies are taking all the data, and they are basically having a big setup to do this training. So I want to just high level talk about what is involved in training, right? You have seen this model dot forward, which I've seen, but that is the only thing that is there in inference. But there are some other things that happen during training. And basically, because you have a lot of data, I just give you this there's a double for loop. So just to give you an idea here, so what you call is there's epochs where you train all the data. So if you have 100 GB of data, you will train everything, and then you will train on it again, right? And you can do it multiple times, because that's how neural networks learn. So they don't really learn in one shot. It is like how we revise a textbook or something, right? It has to read the same text again. So that's why we have an epoch. But within each epoch, you have batches, because you cannot learn everything in one shot. You will learn 4 items or 8 items at one time. So if you see this diagram, it shows like if you have batch size of 1,000, which means everything is going in one shot, right? There will be only one loop. But if you have smaller batches, typically batch size is smaller. Let's say if it's 100, then the entire data will be divided, and in each batch you have 100 items, and you will learn about that 100 items in one go. So that is the core idea of batches and epoch. So that's why this entry. This is the training structure for all neural networks. For anything you do on your local laptop also, if you're learning, and if you have a small, it's not just the thing for large transformer. All the neural networks have the same kind of approach for learning. How do you train? How do you train the weights? So there are other aspects here. So I will just briefly talk about this, because that is important to understand when you scale up for a large model. So the first thing is backward, right? You see here there is a forward. So forward is okay. Now there is something called backward. So what is the backward? What is the idea here? Idea is that the neural network which is not trained will output some value, but you want to teach it to output a different value. So then, like you saw, there is a number of blocks. So in this example, if you see in the left side, so there's a number of operations you can do with your input. But in the end, whatever output you're getting, you want to change that, right? You get some value, but you want to change that value to be more representative of what you want the model to learn. So then you need the backward pass structure. And so I just want to say here is that PyTorch, which is the deep learning framework we're using, right? That provides you the system called AutoGrad, which will automatically figure out the computation for the backward pass. So you don't have to write the code. So you write the code for the forward pass, and automatically the engine will create the code for the backward pass to do the reverse part. And that is, we can use it automatically. Now, the next thing is there, which is involved in training, is optimizer, right? And again, this is the same concept which is there for small neural networks also. But in this case, there is some more complexity because you're learning, but there is a lot of things to learn, right? And you want to learn all this knowledge. And if you try to do it in the most naive way by learning one batch at a time, what will happen is you might go towards your optimal point, but with a very suboptimal path. You might be going in wrong direction. As you train the model, after every epoch, you will be getting a model, but it will be going slowly and converging slowly towards your final answer, right? So an optimizer is basically a component which is having some extra variables and it is having some extra state. And the idea is to allow this gradient descent process to happen in a more smooth manner. So if you take this example, I think it will become obvious. Because of the data, the way the data is structured, you are learning from one point and you're going oscillating like this. So in some sense, you're learning something on x-axis and y-axis, but on the y-axis, you're oscillating too much, right? But with an optimizer, what will happen is we'll have some extra variables, and we can, instead of moving like this in a zigzag pattern, you can move like this, right? Which is what we wanted. We want to go towards your final result. So in this slides, I've used a lot of like references, external references, blogs, and images. Many of these are taken from internet. So I have given the links. And if you're interested in any topic on any slide, you can go follow the link and you can read about it. There is more interesting content there. Of course, I cannot cover everything. So I am only taking some aspects on these blogs. So now, this is the training process. So there are three parts to it. There is a forward, backward, optimizer. Okay, fine. But how to run this, right? So like I said, they're all usually matrix multiplication operations. And so basically you can run it on a CPU also, right? If you have, there are some options. You can run small neural networks on your computer, on your laptop, and it can work. But that is not enough because it will be very slow, right? And the larger the model, the more the computation you have to do. And the more the computation you have to do, the more exponentially more time it will take. Which is why we have accelerators, different accelerators from different companies. I've listed some here, which are helping to speed up your core process of matrix multiplication. You can think of it also as vector processing, right? So your normal computer, you do basically one instruction, one data. But with these accelerators, for one instruction, like you want to add, you will not add two numbers, but you will add a vector of two numbers. So basically you can add 100 items in one go, in one shot. So the hardware is built for this kind of scenario. So the common one, of course, is GPU. Everybody knows about NVIDIA GPU. NVIDIA stock price is so high because it is a very convenient way to do that thing very fast. So that's a very common approach. But of course, other companies have GPUs. Intel, AMD have GPUs, and they have their own software stack, which can be used. You have other companies coming up with accelerators. For example, this picture here is Google's TPU, which is a different chip, which is meant to speed this up. You see here IBM's hardware accelerator, similar logic. This is called AIU, meant for speeding up these multiplications. There are other companies, right? And finally, if you have like the latest Apple Silicon, which is like M series Mac, there is M1, M2, M3. So they have some more. They have their own things they are doing to speed up the matrix multiplication. So they are also good at some of these things. So all of these are required because you can't, if you just run a normal, if you try to do any training or something on a normal computer, it will take too long. So you want to basically speed up your process. So as a running example, I will take this NVIDIA A100, the graphics card, just as an example. Other cards are there. I will talk about this, but just to give you an idea of realistically, practically what goes on, right? So this is an enterprise GPU. This is 2-3 years old, but even then, this is around like I think 20 lakhs kind of thing, one card. So it's very expensive. All these graphics cards are very expensive. It's basically says 80 GB. So we'll talk more about that. That's the memory of this graphics card. Now, inside that box, you have this kind of chips, right? And this is a picture. Actually, here it shows there is an A100 and there is a H100, which is the next generation, right? But you see, it doesn't look that different. Of course, there is difference inside. H100 is much faster. But just to give you an idea of how it looks, right? This is the general thing. Now, if you see on this, even on this picture, you can see on this the score thing is the graphics card. These are some extra peripherals, but the score thing is the GPU chip, right? And on that you can see some squares, right? These boxes. So actually, these squares in this picture, they have actually removed those squares and shown. And I want to call this out because this is what is known as a high bandwidth memory. So these are the memory modules which are there in the graphics card. So what I said, 80 GB. That 80 GB is actually these chips are there, part of this card, right? And there are different providers. So basically, it's not that NVIDIA is manufacturing everything. This will come from other companies also. And you can see this YouTube video if you want to get a more picture about this. Now, this is another, basically another graphics card. This is actually RTX 4090, which is more on the gaming side, right? This, some of you might even have, if you have latest graphic laptops, or if you build gaming desktops, right? So if you see here also is a graphics card. This is also from NVIDIA. This is a different model. This is a different this. But here you see there is actually memory which is outside. So the structure of the memory, these boxes you see here, this is what is known as a GDDR6 version 6 memory, and these black boxes here as the GDDR memory. So this is a different kind of memory. So both are RAM. So both are like what you think as in your CPU, there is a RAM. So for a graphics card, this is the equivalent. But there is some technology difference. So I just want to briefly talk about this, right? So this is HBM stands for high bandwidth memory, right? And GDDR is graphics DRAM. And you see this kind of X-ray vision, and you see like they're pointing out the distance, right? The distance and the size of the card, right? So this is like 110 millimeters, 10 centimeters. So this is the size of the card, right? And you compare that to the HBM, where everything is shorter and smaller. Basically, in semiconductors, smaller is better because you put the things closer. The more closer you put, the more you can get speeds and transfer speeds, and that will make your system faster, right? Basically, this is all about speeding up your training process or your inference process. So it shows another graph here just to show you the distance, the distance to die, right, between the compute unit and the memory unit. And this SODIMM is like our normal one in our laptop, and that you can see is much more much more further. So what we want to show is like there are different technologies in the semiconductor space to make a faster and faster memory accessible. And of course, there is higher speed, but there is also higher cost and higher power. Right? With this, it is more expensive. It also consumes more energy, right, in terms of electricity. And in the flip side, because it's faster, you can run your training workloads faster. Right? So that's just to show you what kind of thing exists, because we want high speeds, and that those high speeds are what is making this current generation of transformers and LLMs possible in the first place. Okay, so now let's look at this memory hierarchy, right? Because this will set it up very clearly for you. The main memory, which is there in your computer, this is your CPU DRAM, and that is basically like you will have, like, you can have large numbers. These numbers are like 1 terabyte is of course enterprise computers. In your machine, you usually have only 32 GB, 64 GB RAM, but this is the speed level, right? And you see, when you come to HBM, your speeds are like 1,000 times faster, right? You're going from the gigabytes per second to terabytes per second. So it's a full one generation jump. But if you see the size, right, it reduces, because that's the cost, right? You're making it faster and smaller, which means you can't put a lot of RAM. You can only put this 40 GB or 80 GB. And of course, inside the compute, there is also the cache like you have in your CPU. So there's a cache which is even smaller, which is only 20 MB, which is like much, much faster. Right? So this is the typical memory hierarchy that you have. But having this is like very important, because that's how the normal computers work like this. But you have to use this, and this example paper, if you see, they use this understanding of this architecture to design your algorithms and design your structure to maximally use all these layers, right? Because that's what exists. So on a GPU, like we saw the A100, these are some cores. So basically on that GPU, there are a lot of these SMs. There are actually like 128 SMs. So 128 copies of the same box. And within that also, there is like further units. I mean, just trying to show you what kind of happens inside a GPU, right? So that GPU is not a mystery to you. So GPU is just another computer hardware with special design, right? So they have a caches like you have in a CPU. And then they have all of these, lot of these units, like this is int32, so it's units to do int32 processing, which means an integer which is 32-bit size. You can have floating point 32-bit size, and so on. And you also have these tensor cores, which are very important, because these tensor cores support the matrix multiplication operation, which is very common in our entire transformer architecture. In all our LLMs, this tensor core is used all the time. So again, I've given a link here. If you're interested, you can go look into this later. So this is basically a repo which talks about different like kernels to do this matrix multiplication. very efficiently using those APIs. So it's basically there's an API under CUDA. So CUDA is the software layer, how you write the code so that it can run on the GPU, and you can basically use this API to use these specialized units, and that will run very fast. It will do a matrix multiplication of a large size very quickly. So now basically I'm talking about this. I've showed you GPUs and diagrams. We talked about the memory and the compute, right? So like a compute, for example, if I take a GPU, they might be 128 SMs. Each SM will have some capacity, and that will totally, we can say that's a teraflops per second of that GPU. Similarly, there's a memory, which is like the 80 GB like this that I've shown. And now what is the thing is, if you don't have enough compute, like even in your laptop, then if you run a task, it will just take you longer, right? But it will run, it will take you longer. But if you don't have memory, you can't even fit, like you can't even start the thing, or it will crash, the process will crash. If you go more than memory, it is not possible to run something. So these are important patterns to keep in mind, because everything you do after this is based on this, right? All the training and the inference and stuff. So when you do a training, there is a certain kind of compute and memory pattern, a flow that happens behind the scenes. So this graph is just trying to show this. I mean, all the details are not important, so don't worry about all these numbers and all, but just try to see the shape. That's what I want to show you here. So basically you have your model weights, which is, I think, the green portion, right? So the green portion at the bottom, this is your basic model. And this is your model weights that you load. So this will always be loaded. So when you do a training, you'll always load these weights and keep it. Then you have some stateful optimizer, like I said, that's the yellow portion. That is also something that is just constant, some amount of data it is going to take. Apart from that, we have the red and the blue, which is actually the activation and the gradients, which is what we were talking about versus the forward pass and the backward pass. So the forward pass, as the forward pass happens, there is some activation created. That's what is shown here also. And then when the backward pass happens, you basically give away these activations and you compute gradients. So all of these you can think of as the intermediate results of the matrix multiplication. What happens after each layer, and what are you storing, because you want to learn the weights. So that's what you store. So you create them on the fly, like after every layer. After you use them, you can free them, right? But that's the in a certain kind of time, for certain few milliseconds or seconds, you need to keep that memory. And if that memory is not going to fit, then you cannot do it. You cannot run, right? If your memory or your machine is not this much, you cannot even run this process. So there is this pattern, and this is how the memory is being used, right, when you do a typical training flow. So how much memory, right? That question will come. And I've given some approximate numbers, but for you to get an idea very clearly. So you will know models are of size, a certain size. Usually it's in billion and trillion these days. So this is the parameter size of the model, right? So if you've used models like Quen, like you might have heard of a model called Quen 32B. So that means 32B is the size of the model. And this 32B is saying that it has that many parameters. So these are the weights that it has to learn. So these are all being loaded. So when we say those are the parameters, this is the green portion, which will be eventually loaded. Now, each weight is basically a floating point number. That's what it is, right? It's a floating point number. By default, let's say is assume a FP32 data type. Means each floating point number, it can be represented using 32 bits, which means 4 bytes, right? So the model weight itself for this 8 billion model, if we take, it is actually 8 into 4, around 30 GB. And now you can do similar calculation for how much the gradients would be. Like gradients also actually will be stored in FP32, then it will be 4 bytes. Optimizer state, for each weight, optimizer will actually have 3 values. So it has that momentum and variance. As an example, with the Adam W optimizer, there are other optimizers. So they will then store so many bytes per parameter. So basically you can do calculation. And of course, on top of this, you have activation, which is depending on your batch size and so on. But that's, you can imagine that that's something more than that. So let me just reiterate on this, right? So there are tools to estimate the size. So let's take some simple examples. Some of these are, this Granite 2B is an IBM model. So it's a 2B size, which means weights alone will be 7.5 GB, gradients will be 7.5 GB, optimal will be 22 GB, total would be 37 GB plus. There will be something for activation, right? And so when you load the weight from Hugging Face, because a lot of these models are available, they are open weight models, what you focus only is on this column. So this is the weights, and you can see, and this will be compressed, but you will download the 7.5 GB if you try to download a model from Hugging Face. Similarly, I've shown some other models, right? And you can see it is adding up very quickly, right? When you go to 32B model, you are getting like around 600 GB of memory for the training process, right? So if you just want to do inference, maybe just you need this first column. But when you do training of the weights, you need all of this. So you will have around 600 GB in this case, right? But now see the problem. I've showed you some example GPUs. A100, I was showing you 80 GB. H100 came like maybe one last year, 2 years back. B200 is like the current latest model. Next model will come. But you see the kind of amount of memory we have available, right? It is not so much. It is, you're ranging from 24 GB, which is like high-end AMD card, and you're coming up to 180 GB for the latest model. Of course, this is a very expensive model. You cannot even purchase it because there's a big queue of people waiting to buy this model, and so on, right? So basically our problem is, no matter what technology improves, at the level of the GPU memory, HBM, we are in this space, right? Around 200 GB maximum we have reached per GPU. This is what we have. But now compare that to the various models we have today, right? I mean, I'm taking some frontier model examples. So Cloud Opus 4.6, which is like the latest model. ChatGPT, sorry, this should be 5.3, not 4.3, 5.3 latest model which has come out. These are like closed models, of course, but they are very, very big. They are trillion plus in size, right? So you can imagine the size here. It's like, I don't even want to write it down because it's so big, right? And that is just this column. And now we have all these columns, and that's into 3, and it will be a very big number, right? But these companies have trained these models, and how do they do it? So that's the thing. Today, in today's session, we're talking about how the distributed training happens. These models, for example, are also very good models. They are open weight models, so you can actually get these models from Hugging Face. But they are a bit smaller, so obviously, they may not be as good quality. Generally, larger the size, you have more quality and the better outputs that you have, right? So this is the overall picture of the weights, of the size of the memory, existing memory availability, and the challenge, right? Now, before going to distributed, right, I want to give some comments about what you can do otherwise if you don't have so many GPUs. What can you do, right? What are the different things you can do if you have only a fewer number of GPUs? So the first thing is, we talked about the optimizer, right? So the different softwares optimizer. I talked about example of Adam. There's other optimizer like SGT optimizer, which doesn't do into 3, does only into 2, only 8 bits. But that means you lose some of the learning capability, right? It may not learn, the model may not learn that way. So maybe it will take longer for you to train the model. Another option, you might have heard about this word called mixture of experts. This is a different kind of model. There's a new architectures. So there is a research space. There are new model architectures coming out. So those kind of things can try to help by reducing the number of parameters, right? Which means then you can again try to fit the train. But the problem is, for MOE, especially, at least for training, it actually doesn't help. It only helps for inference. So while giving the model out, then it helps, but not for the training process. During the training process, you still need the full size. Okay. Now there is one more aspect here, basically about off precision. I want to talk about this because this is also very good to know. Normally, in our CPU and all, we usually just go with 32-bit word size. That's the normal thing, 4 bytes. So this is very common for us. But because of this, the trouble and the amount of scale, these GPUs and other accelerators actually focus on smaller, reduced precision. So we are talking about using 16 bits to store a floating point number, which means you're going to reduce, the exponent and the mantissa portion. You have lesser number of bits, which means, you cannot represent all the floating point numbers. You're reducing the range of floating point numbers that you can represent, but that may be okay because you're losing some accuracy, but with that, you're actually gaining speed. So these are very common. There is also even smaller FP8, 8-bit, and so on. And every time there is basically a reduction in accuracy, but it's okay because the training process will take care of that. And these things, these different data types, basically these are different data types for floating points. They are not just like to storage. It's not just about saving the storage and saving the memory, but it is also about saving compute, right? Or faster compute. So for example, TF32, you have hardware support from the GPU, like NVIDIA GPU has some units which are actually doing computation specialized for that type. So basically, instead of having the normal type, you have some other type, and you have hardware which is faster actually. And it is actually a nice table I can show you here. This is from the same A100 chip we were talking about earlier. When you do FP32 computation, you get 19.5 teraflops. So basically, that's your speed or number of computations you can do, right? When your each computation is FP32. But if you go to FP16 tensor core, you see it's actually 312 teraflops. So it's much higher, right? You're able to actually go to a larger computation ability, because each unit will be smaller in the hardware, right? If you zoom in into the nano scale, you can fit more of those computation units, like arithmetic units and so on, because you are dealing with lesser number of bits. So you can fit more computation on the same chip, and that's why you can get more speed and more capacity. And this is very useful. And also the same space saving helps in memory also, because earlier what would take 40 GB will now only take 20 GB, because each floating point is taking lesser size. This is one more, just another datasheet example. You can get these kind of data sheets online for different GPUs, and it is very nice to see these numbers and compare and see how they evolve over the years, right? There will be newer and newer GPUs, and you can try to compare this number with the previous number, and see they have actually improved over the years, how they're improving the speed and so on. But the point is, even with all those improvements, every GPU is getting improved. Every year we're getting better GPUs. Even with all of that, we are still going to be stuck with that 80 GB or 100 GB, which means we cannot really go further, even if we're ready to wait for longer. So like I showed you this earlier, this is an SM just to show you the scores, tensor cores inside. Now, one more technique to do if you don't want to go scale up is basically you can do something called automatic mixed precision, where, like I said, instead of moving everything to 16 bits, you can move some to 16 bits and keep some in 32 bits. So all this basically is trade-off, right? You're trying to find the best combination and seeing that what works better, trading off between your compute and memory. So, but of course, now you can only do so many things without multiple GPUs. So we have to go to multiple GPUs. So then the rest of the talk is about how you're going to use the multiple GPUs, right? Because it's not easy. Other option is to actually reduce your model, like we saw. You can make to 16 bits. People are going to 8 bits, 4 bits, and things like that. That is also an interesting area of research, and that is more relevant for individuals, right? You can try to run a big model on your own laptop. So there is research and approaches here. But today we'll focus more on the industry side of things, which is the distributed training, because industries can just afford more bigger clouds and more GPUs. So this is like a map of what are all the techniques. I just flash this so that you get an idea. You can go look about these things later, right? So on the left, actually, you have the various algorithms. The algorithm is what is the logic? How are you doing the training, right? How are you splitting up? On the right, you have actually systems, which is what is the software, what is the code, what is the library that you can use to do these things. So there are different libraries. Many of these are open source. After the call, you can go and see if you're interested. You can go look at this code. They're all available. That will give you an idea of how these companies are doing things. But the left is the logic. So if you understand the logic, you can think about and understand more papers are there in this space, how different aspects and why, right? So that we will focus more on this algorithms, but just for your awareness. So let's start with your most basic, simplest technique, right? So basically, does your model fit into single GPU, right? And of course, by model, I mean model plus optimizable gradients, except the activation part. If so, then the simplest thing we can do is what is known as DDP, which is distributed data, right? So data parallel. So what you want to do is you want to split up your data. Instead of, because your one GPU cannot handle all the data, you buy 5 GPUs and you give different parts of your training data to the different GPUs, right? That's the idea. Now, why? Like, let's just talk about this again, right? I told you there's some GPUs with 48 GB, some GPUs 80 GB, and we are assuming your basic model part is fitting, and this can fit because, like, it's an 8B model or 2B model, and it's able to fit all of this within this portion, right? And so the rest of the portion of the GPU you can use for your data. So basically, if I only have 48 GB, I can set batch size to 8. That means I can fit the activation maximum, and then I can keep doing. But if I have more in that one GPU, then I can take back 64, which means in that same time, right, I'm able to do, like, into 8 batches. So if I'm able to finish off that many batches more, then I can proceed and I can finish my training faster, right? But you can see here that I know after 80 GB, you can't go much further, right? 100 GB, 150 GB, but you can't go more than that. So you really can't scale like vertically, which is where we come into this horizontally. So in standard enterprise, it's horizontal scaling versus vertical scaling. So this is kind of vertical, where you try to improve the capacity of each instance. In horizontal scaling, you're going to throw more instances and then try to split your data to work with these different instances. So now if you see here, I will just talk about this again. This is the same thing we talked about earlier: forward pass, backward pass, optimizer state, right? I think all these words you would know now. So basically we have input, which is the data, and you have the model weights, and then you have the forward pass operation that happens. Then you have the activation, like I said earlier, it is created in the middle. And then you use the activation in the part of the backward pass to create the gradients. The gradients is basically telling you how much the weight should change. And then you go to the optimizer and you get updated weights. So this is the normal flow when you have one GPU. So when you have one GPU, this is the flow. Very simple, very straightforward. Now, how can I split up, right? What should I split up? So because we said everything fits, so basically we can load all the weights, same thing, the weights on all the GPUs. And let's say basically we run the forward pass on all the GPUs, right? That is also okay, because we are able to fit on each GPU, we're fitting some different data set. It's okay, it's fitting, it's doing. Then we can run backward pass on all the GPUs because everything is still fitting, it's all fine. Then when you run optimize on all GPUs, what will happen? What will happen is each GPU will have a separate model. You started with one model, but if you had 5 GPUs, you ended up with 5 different models. But that's not what you want, right? We want to do horizontal scaling because we want to learn all the data in one for one model. We want to basically create a new improved model, or this is how they do the pre-training. So you want one model, you don't want 5 models, right? And you want one model which has seen the data on all the 5 GPUs. So that's why it's a problem. You cannot just simply split up and simply say, I will run this identically on all the machines, right? So there you have to change the protocol. And this diagram is showing what is happening. On four GPUs, the first forward pass and the backward pass will happen exactly identical independently, right? With different data inputs. So basically you have 100 GB of data. You split the data and you take the first 25 GB, some files, something, and the second 25 GB, and you give each GPU separate data. So the forward and backward can go in parallel independently. They are all doing different things. So at this point, each of these GPU has some gradients, right? Each of them has some gradients. They are all different values because they are all based on different inputs. Now we have to do a synchronization process to convert all this gradient into synchronize, so that they all actually have the same value, so that then the rest of the operation, when it happens, you end up with the same weights. So actually you just want one weight, right? You don't want 4 copies of the weights, but the computation and the memory is not enough, which is why you're splitting up, right? So in this process, what we're saying is, if we synchronize at this stage, whatever is the gradient size, so let's say gradient size is 12 GB, so there will be 12, 12, 12, 12, so total 48. But after the synchronization, each will have only 12, right? And it will actually be the same value. So the synchronization is basically adding up the value. It is not putting it together. So instead of like you have 12 GB, 12 GB, you're not concatenating the value, you're actually adding the value. And why is that okay? Because that is actually the normal way that gradients work, right? Even in a single GPU, when you have a bigger batch size, you have batch one, another batch, then they will have different level of gradients. You can simply add the gradient because you're telling that you're trying to teach the model all these different things, right? So you can basically add those gradients. So the thing is, the first 2 steps is like identical and independent. The third step will do the synchronization, and then after that, actually all the 4 GPUs will do the exact same computation, the optimizer part, with the same input. All the 4 Gs will be the same now. They will go through the exact same process and they will end up with the exact same weights. But this is the way, because of that for loop. I had showed you there is a for loop, double for loop. The next part of the for loop will start, and then this whole thing will happen again. That is the reason for keeping like the 4 copies of the weights, because otherwise you have to again do some copying and all that. You want to avoid those things. So each of the GPUs will have weights and they will simply loop. Okay. So like I said, synchronization is basically very simple for gradients. So that's not true for everything. For gradients, you can simply add the gradients because that's how much you're changing, how much you're training the model. Now, I said easily add the gradient, right? But that itself is a big problem because, like we said, it has like number of params into the data type. If it was BF16 or TF32, for 8B model itself, it's around like 25 GB of data. And now we are saying I have 25 GB of data on 4 GPUs, and I want to add them all up, right? So this, if you do it naively, this will require one more GPU, because where are you going to store 25 GB into 4 amount of data, right? And you don't have space. All the GPUs are already occupied. You have to add them all up. So there is a lot more work, right? So how to do this efficiently? Actually, that's where the concept of collective comes in. So in this case, basically we have something called all reduce NCCL. I will talk a little bit more about this, so don't worry about it. So the point is, the GPU itself, the hardware, the architecture, the software, they are giving you some functions to do these kind of operations on group of GPUs. So earlier the normal computation happens on single GPU, but we want to do things across GPUs. So they are giving some inbuilt operations. Basically, these are known as primitives, network primitives, and that is usually packaged as this thing called NCCL. So NCCL, of course, is about NVIDIA. So we are talking about NVIDIA GPUs. So that's why I've taken this example. CCL stands for Collective Communication Library. right? So that's the core thing to focus on. Other company have their own library. Intel will have its own library. Other people have own library. But NCCL is a very famous library because NVIDIA is very famous. This is the homepage if you want to go learn about it. So it is give you some tools to do multi-GPU, multi-node communications. Right? That's the point of this library. Now, like I said, there is also like communication between CPU cores if you want. So this is like Glue. You can look at this library. This is something you can run in your laptop because it is about CPU cores. It's a very active area of research. There are research papers about improving this communication. So just to give you a broader thing, we will talk only about NCCM today. Okay. So what does it? How does it work? So you have to, in the library, you initialize a library. You have to create a group. It's called a group or a world. You can think of it like that. And that is a group of 4 GPUs or 8 GPUs or something, right? So in this case, I've taken 8 GPUs. Each GPU has a rank, and that rank is going from 0 to 7, right? 0, 1, 2, 7. So every GPU has a rank, which is its own ID, right? Number. And you have a total number, which is 8, which is the world size, the number of GPUs. So this you need to know. All the GPUs need to know before they start. So when you run the command in PyTorch, there are some flags to inform the process. You have to start 8 process, let's say, and each process you give the flag that, I am rank 0, I am rank 1, etc., etc. And that is required to do the communication, etc. afterwards. Now, what kind of communication, right? So very simple example we'll take. Simplest thing you can do is P2P, which is point to point. So we have 4 GPUs, let us take. And the communication we want to do is we want to send some data from rank 0 to rank 3. So this library will have functions to allow send and receive. So you have to call the send function. So there is a nice tutorial in this URL. You can go check this out later. This is something you can run on your machine also, I think, because you can run it with Glue instead of NCCL. But idea is you can start 4 processes and you can send something from one process and you can receive in another process. And the library will take care of how to transfer the data, right? So that what you might ask, what is the challenge, right? You can do it on CPU also. What is the challenge? Challenge is it has to do it very fast manner. It has to be very, very fast. And it has to be also very no overheads, right? And as fast as possible by using whatever hardware is available and so on, right? So actually a lot of work has gone in the NVIDIA GPUs. I will show you some pictures later about how to make it fast, right? And all of those things are important because every second counts. With all the optimizations also, training a new model takes like 6 months. And I'm talking about like hundreds of thousands of GPUs, right? Not like not even just thousands, 100,000s. So we are talking about big companies, Google, or even we have our own models. You have Amazon, you have Twitter. Each of these companies have clusters, big clusters with like thousands of GPUs, and they have to do, even with that many GPUs, it takes like 3 months, 6 months for the next model, right? Which you can see is a very, very long time, even with all the optimizations. So every bit counts, every optimization counts. Sending has to be very efficient. So this second set of operations is a collective operation. Instead of doing point to point, we are going to do collective operation, which means there is going to be some data on each GPU and there is some operation which you run, and the result will again go to multiple GPUs. So it's like not just point to point, but the group itself is designed to do something. So this example is actually scatter. It's an operation called scatter. So where we are saying the rank 0 first GPU as an array of 4 items, let's say, and after the operation we want one element of the array to be there on each of the ranks. So you're actually splitting up. You're basically scattering the data, right? So this is one collective. This is one operation. Right? Let's say different operation, gather. So these terms are very like common distributed things. This is the same kind of concept that has happened in earlier data processing that you might be aware of, like Hadoop or things like that. This is the same fundamental concepts, but here it is about GPU specifically and how the GPUs are communicating, right? And also keep in mind, when we say GPU, we are saying GPU memory, right? So your machine might have a lot of memory, but your GPU only has 80 GB, and you're doing this operation from GPU memory to the other GPU's memory. That's the idea. You are trying to reduce the path, the speed, right? You want to reduce the time it takes to do this kind of communication. So gather is basically a reverse operation. So each 4 GPU has one item, and you want to gather it together and make an array, right? So this is an example of gather. Reduce is an example where you have one item on each array, and you want to do an operation, and like for example addition, and you finally have a result which is there on one rank, right? This is actually not used very often. This one is more used often, which is the same one we saw, the distributed data the parallelism technique, DDP. It uses all reduce, where what we are saying is gradients we saw, right? So each rank has its own gradients which are different. After this operation happens, each of them actually has the same thing, which is the sum of all the 4 values, right? And internally it will find the most efficient way to do this, so that we have the sum, and we are not doing the sum again and again, or we are not wasting extra memory. See, if this is 25 GB, this itself is 25 GB, right? At no point will this have 100 GB, right? The operation will take care that You start with 25 GB and you'll end with 25 GB. That's the only way it can work. There is no free memory. I cannot collect 25 GB from you, 25 GB from you, and then add. I can't do those things, right? I have to do the thing in network, in the hardware. So that's what this is giving you. This is providing you. This all reduce is very common operation in distributed training. We saw one. All the algorithms pretty much use all reduce. It's very common. This is another example of all gather. This is used in some algorithms, but you can get the idea, right? These are the collective operations. So now I will again come back to this point, but this is very important to note that the reason for doing this, the reason for using NCCL, is there is a lot of underlying hardware and software which is doing special things to support this. For example, it has dedicated hardware routes, bridges, and switches to make it fast. It has topology. So when you see these 4 or 8 GPUs, they are not connected all to each other, right? They might have a tree connection. So these are the same concepts you might find in other places, like in networking, in switches, and in data center management. It's actually a very similar concept. If you understand those concepts, you can understand this also. But this is specific to the GPU and the GPU hardware that is there, right? That's the difference, and that's why it has more bandwidth. It is larger in size. Those are the kind of differences. But that's the core same concept. So now we saw DDP, which is one technique, right? And it's a good technique. It's very easy to use. It's a very good technique in that way because it is very easy to write the code for it and it works. But there is a problem, and that problem is when you do the synchronization of gradients, in the end of the day, you are getting that you are basically putting all the gradients back together, which means your batch size is equal to the total batch size. It is almost as if you had only one GPU and you had batch size of like 16. Now you have 4 GPUs and doing batches of 4. Right? So the total batch size is you're going up vertically. Well, so the problem with this is from a deep learning point of view, right? From an algorithmic point of view, using larger batch size is bad because that leads to overfitting. So actually, you want smaller batch size. Ideal, obviously, small is also too bad. You need to fit in the right place, right? So you cannot really just keep increasing batch size, and that's not good for the learning, right? You need something different. And the other option is, of course, like I said earlier, we are basing the model to fit on a single GPU, right? That's the minimum requirement for this algorithm, which is a big problem because it doesn't. Like we saw the models, like they're all 600B or 1T and there are terabytes. So there is no way that I'm going to fit the entire model in one GPU on 4 GPUs, then each model will have a copy. That's not going to happen, right? This is a bigger problem. Right? It is never going to happen. We have reached 5 years back. This was not the case. 5 years back, our models were small. GPT-2 was like only 125M, that kind of thing. It was able to fit, right? Now, every year, models are becoming bigger and bigger. So we need new algorithms. So that's the way actually all the algorithms have come up. Some problem has come up with the old algorithm that is not going to work. That's when new algorithms have been proposed and then implemented. That's the idea. So now I'm saying the first thing I'm saying is the model is not fitting, right? The model is more than 80 GB. So there is no way I can, copy. So the only option I have to do is I have to split it down, right? And this is problematic because you split the model. It's not easy, right? I am saying split the model. If you just want to store it, it's okay, right? If you want to store it, I split it into 4 copies. I store it, I'm done. But we are actually doing computation on the model, right? We are doing some matrix multiplication. We're doing some vector addition, all those things. So if you just split like this, you can't just split like this and go. You have to split it, but you also have to come up with a new algorithm for the computation of how you are going to do the computation with that right? Basically with the split parts. So you have to have a new algorithm which is taking the split part and doing some computation, and the final answer has to match whatever was the original thing, right? So that becomes a challenge in all the algorithms after this. Basically only the first one was the easy one. Everything after this, you have to do something. You have to update the computation. So now we will start with the simplest one among this, right? And this is basically this right one. So basically we have 2 options. You can cut it vertically or you can cut it horizontally, where each of these are the blocks that we saw in the very first slide, right? So this is the block, but we're cutting the block. So for example, all of these models have the same block repeated 32 times as an example, right? They'll be 32 or 16 or 64. And those blocks have different weights, of course. So actually, if you open the code and if you open the weights, there will be different values, but the logic and the algorithm will repeat, right? What you do for one block will be the same for the next block and so on. But like I said in the very first slide, a forward pass itself is basically once through all these blocks, right? And then another forward pass would be again through all these blocks, and then again through all these blocks. That is just the forward pass. You have backward pass, you have optimizer, all that also connects to this. Okay. Okay, so now we will split the model horizontally because that's the easier thing to do. And what we're going to say is, let's say we're going to split up. Let's say like I said, we have a world size, right? So, and I know, like I have 8 GPUs, and that means I have 8 into 80 GB, right? So basically, I can split up the parts so that each of this stage, so basically what when you do a split, each of these horizontal line we're cutting is a stage, and inside a stage, of course, there can be multiple blocks. Wherever you want to cut, you can cut. But the idea is that one stage fits on one GPU. Right? That's the minimum requirement. Otherwise, it is not going to work. Right? So one stage has to fit on one GPU. That's the way you split up your layers. Okay, and now this can be confusing. So I want you to think about this. This is the core pipeline parallelism algorithm, and basically let's just start with a very simple thing, right? So the F is all forward, right? So we have device 0, 1, 2, 3. So in this example, you actually have 4 GPUs. That's what we're saying, and we have some split portions, right? But if you see the split here, the very first part, so even in the first forward pass, a forward pass normally would go through this entire thing. Let's say, let us take this example 12, right? There are 12 decoder blocks. So normal forward pass would go through this entire thing, which means what? Input comes in, there is some computation happening here, so then output comes in, then there is some computation happening here, then output comes in, and then it keeps going. Okay. So input for every block is the output of the previous block. So we cannot, so if I say the 4 devices, I have the 4 devices, and I want to do the forward passes, there is an ordering between them. Actually, that's what this arrow shows. You cannot run the forward pass. In the previous case, we had a diagram with the distributed data parallel. We were running the forward in parallel because they were different inputs. So there actually what was happening was there was different input. There was an input coming here for the first GPU. Another GPU has the same exact 12 block copy, and different input was going. So at the same time, both the GPUs can work, right? They can compute because they have different inputs and they're not dependent on each other. But in this one, there is only one input which goes to the first guy, the first stage. That means rank 0. So this device 0, this F0 is the very first thing you want to think about, right? So this is the forward pass. So you say some matrix multiplication is happening, something is happening. Okay. Now, output of this stage will be the input for the next one. So that's where this arrow you're seeing. So you have to wait. Device 1 cannot start. Device 1 cannot start. Device 1 will be waiting. And when finally this one is done, it will do a send. So this is where we saw the collective communication, right? So the send receive, we can do a send receive. So the first device, after it is finished its work, it will do a send. The second device will do a receive. It can do a receive in the very starting because it is waiting. Receive is like a blocking call, right? You're saying, I am expecting some data to come from GPU 0, and I'm going to wait until that, right? And that doesn't waste any computation. You're just waiting. So now then the data comes, then it can do the forward pass. Okay. And once it doesn't forward pass, it gives output, then it goes to the next device. So this is basically stage by stage by stage. You're doing one after the other. When you're done with the last one, you have the loss computation, and then the loss backward will start, right? So when backward happens, it will do in the reverse. The way backward works is when you do forward, your forward goes like this. Obviously, like it is visible in the name itself, backward will go from this downwards, right? So backward will do processing, and it will keep the reverse, right? The output of the block will go to the next one. So it will go in the reverse order. That is the normal structure of backward. And every time backward happens, it requires the activation. Like we saw earlier, it requires activation for those stages. So basically for this stage, there will be some activation stored. That's that memory that in the graph that you saw, there is some memory being stored. And until the backward happens, it has to store that memory. So when the backward happens, it has to actually happen on the last device, the rank 3 device. It will do the backward. And when backward is done for this one, the output of it, the gradients, will flow to the previous stage. Right. So in the backward, you actually have the reverse order. So you go the forward device 0 to 3, and you come back device 3 to 0. Right. And when you're done with the gradients, you can then do your optimizer state. That's different. So there is another diagram here which you can look, which should make it very obvious to you. This is a core diagram for pipeline parallelism. If you understand this diagram, everything will be easy for you. You can easily follow. Right. So we are saying first, so this x-axis is time, right? So first what happens, only F0 happens. The other GPU. So basically this y-axis is showing what GPUs are doing, and the color code also is used for that. First, the forward pass happens of the first GPU. Other guys are doing nothing. That's why this empty space is there, this blank is there. Next instant, after the first thing is done, maybe that has taken some 5 seconds, right? After the 5-second period, now this guy work is over. It will simply give away the input for the second GPU, and it will sit simply. It cannot do anything. It cannot do the backward pass because it requires input to come back, right? So it cannot start the backward pass. It will simply wait. And the first GPU is doing work, other guys are free, right? Then same thing happens here. So basically you have to see the white space. If you see this rectangle, the white space are portion where nothing is happening. That GPU is actually free. The color spaces are portion where that GPU is doing some work. Okay. So in this is a diagram for 4 devices. So 4 forwards happen, then 4 backward happen in this order, reverse order. And if you see here, one more thing I have to note here, you see the backward is rectangle. it is bigger than the forward rectangle. So forward is actually like a square, but the backward is like rectangle, double the size, right? You can see the size is not the same, and that is important because the actual computation that happens is different, right? In forward, what happens is different from what happens in backward. In backward, there is actually more matrix multiplication. Loosely, the backward takes double the time for every forward, loosely, approximately. So not 100% correct, but you can take it like that, right? So point is, if a forward takes 5 seconds, backward will take 10 seconds. So you have to include that in your showing the waiting time. So when this is wait 10 seconds, the other GPUs are waiting. Okay. Finally, optimizer state will be there on all the GPUs, and they can all do the update in parallel because they all are talking about different parts of the weights. So the optimizer is updating the weights, correct? So this two stages, these decoder weights are only there on the first GPU. They are not there on other GPUs. So it can update easily because it has all the data it needs. It has the gradient. So after the backward happens, it has the gradient. It has the weights. It has all the required state for the optimizer. So all the four can do the update in parallel. And that portion is actually, you are not waiting. You're not waiting for anybody. And this will take the same time, right? Because of the same size. And when you're done with this update, what has happened is you have done your one batch or one epoch, right? One batch basically. So your one batch, in that for loop that I showed in the starting, that one batch is done. So then you can again go in a for loop many times, and the whole thing will repeat, right? That's why you see the weights, because the weights for these stages are there on the first GPU. They never move out of the GPU. So when you load the model, you load, I have 80 GB weights, or let's say I have 200 GB weights. The first GPU will get 200 by 8, only those weights. And those weights will keep updating with this whole computation. We have split our computation and our memory so that each GPU can do its own thing, and the weights are there. There is no other network communication, right? We are not doing any synchronization. So in the previous example, we are doing synchronization of the gradients, right? So here we are not doing that. Here we are doing simply send and receive. So this one doesn't use the synchronization part. It uses the send receive calls. Okay, so this is just some text description of what is happening. I have actually just explained this thing. Maybe this diagram also helps. It's the same version. Now inputs, there's only one set of inputs that goes to the first GPU. Then the output of the first forward pass is the activation that goes to the next one and the next one and so on. And in the reverse, what actually happens is gradients. So there is gradients that is being transferred to do the backward pass computation. And finally, we update the weights. So you have a updated W on each GPU. This whole thing can repeat. So this while talking itself, you might have realized there is a problem with this pipeline parallelism, and that problem is, like I said, this white space, right? So this white space is basically time where some GPU is idle. It is sitting there and it is not doing anything, right? And like I said, we are talking about data centers with 100,000 GPUs, right? So that's a very expensive. This is expensive hardware. You don't want it to sit idle. You have spent so much money on each GPU, and you want to use them more, right? You don't want to waste them. If they're just sitting like that, then you're wasting. You're wasted your capex, right? You've spent money and bought a GPU, and it's sitting there and it's not doing anything, right? So there are a lot of techniques which are improving upon this pipeline parallelism to actually make that thing more efficient. Actually, I have not even shown the first one. The very first one is this pipelining. You might have realized in computer architecture also, you might have seen this concept of pipelining. So here, actually, there is no pipeline. They're all waiting, right? A real pipeline happens when this kind of thing happens. And here, what we are saying, first batch forward passes happened. Then it is sending the activation to the second GPU, right? But now the first GPU is free. It can start doing a forward pass for a different data set. So basically, you take a next input, next batch, and you start doing the next batch forward, right? And next timestamp, what will happen? This forward, the first forward for the first batch is over. It will go to the next GPU. It can basically take the output of the previous one. So it's basically this diagonal line that you see can repeat again and again, right? So this is basically what we're doing is we are trying to actually fill this gap. So this bottom portion, white space, we are trying to fill the gap there by doing other computation, some other computation, right? Which for where we're doing that for loop, we're taking the next iteration of the for loop, and the first guy will start on the next for loop. The other guys, other GPUs are still waiting. They are still in the first iteration of the for loop. But this guy, because its portion is done, it can start on the next iteration of the for loop. That's the idea, right? And the same thing for forward and backward. So similar logic you have for backward, right? The same diagonal update. And finally, you have updates, right? What you're doing in this example, what they actually do is they call it a mini batch or micro batch. So they take an individual batch and again split it up. But okay, the word is the same, concept is the same. Batch is what you're operating at one time. So you're operating on multiple batches in a pipeline manner. So this is the standard pipelining that you see in computer architecture. It's the same concept here, which is happening across multiple GPUs, right? And this is actually some very basic, the first thing you can do. By the way, the word for this is called bubbles. So the pipeline bubbles, I think bubble is the same word in computer architecture also. Here also it's called bubbles. And the aim is for you to minimize the bubbles. Any white space is a waste. And there are many papers, many approaches. What I've explained is the basic algorithm. In the end of the slides, actually, I have examples, some more advanced algorithms. But you can imagine, you can go search about it, and there are many papers which are available. They talk about how to do change the schedules and how to do fusion and things like that to reduce this bubble size. It's that important problem that a lot of effort is spent on. Now, you might ask that instead of doing all that extra work and removing the bubble, can we do it in a way that bubbles are not even there, right? Why are we? Can we just not? Can we avoid the problem in the first place? Right? That's a valid question, and that actually is this other approach, the vertical cut that I skipped in the beginning, right? So we did a horizontal cut. Now we are doing vertical cut. So why I am saying that vertical cut means bubbles won't be there, right? Why are we saying that? Because when you do vertical cut, all the GPUs will have some work to do, because after every stage, you see here earlier we had a stage, and because the stages were horizontal, every stage depends on the output of the previous stage, right? That is why the third stage has to wait for the second stage, right? It cannot go because it has to wait. But when you do vertical cut, what we are saying is stage one will get split up vertically. So different computation will happen in different GPUs. But to go from stage one to stage two, each guy has its own data. Right? You are not some guys. There is no imbalance. Basically, there is compute balance. That's the right word. Between the process, there is complete balance, because at any point of time they have something to do. They have some work to do. Okay. Now, it is easy to say I will split vertically, but actually splitting up vertically is a very complicated process. Next few slides, I have some details about this. This can be very confusing for the first time. I will try to give you the intuition. I have some code also here in the next few slides. So if you are following, if you're able to open a Python terminal and you have NumPy, there are some commands here that you can copy and try. This is not compulsory. I'm just giving you this option. If you do it hands-on in the next 5 minutes, just copy and paste those. Basically, just type those things in. You might be able to get a better feel. Otherwise, you can do it later also. But just to give an idea, because splitting vertically is much more complicated. Splitting horizontally, we saw the logic is actually quite easy. Splitting up vertically has more problems, right? And the next few slides, we will talk about that. If you have Python, if you have NumPy installed, just open a Python terminal, have the NumPy open. I'll show you some slides and some commands. If you run it, you can see the matrix sizes and shapes, and you might get a better intuition for this. Okay. So this is the transformer layer we're talking about. This is one layer or block, and there are many blocks, right? Like I said, there are all these decoded blocks. So there are 12 blocks. So there will be 12 of these blocks. Okay. So if we figure out how to cut any one block, it is the same for all the blocks, right? So we can focus on one block. And inside the block also, I told you there are different blocks, attention layers and things like that. So again, there is slight logic difference, but we can focus on just one of them, because again, whatever we learn here, same will apply there also. So if I focus just on the MLP block, I want to zoom in for the next few slides. I'm going to zoom into this MLP block, which has actually these 4 operations, and just think about how to vertically cut this, right? That's it. We will just think about that, and that logic will apply to all the blocks and everything else. Okay. So what is happening in this block? Actually, you have this kind of operation. You start with an input X, so that's what is going in, and then you have a matrix multiplication. That's what is showing XA. So whatever is input is getting output of that layer. I could have kept more variables, right? I could have called this X, Y, Z, W, but in this I've just shown this. Just imagine output of each one is going to the next one. That's why X is getting updated. So GELU is the next layer. This is a typical thing in neural networks. Then you have another matrix multiplication. So this XB, and then you have a dropout layer. So this has to happen, right? So now cutting, when we say cutting the MLP block vertically, I have to cut each of these vertically, right? That's how it will work. I cannot, how will I cut it? Now, this is the example code I have said. If you have a terminal open, you can just try to run this. I'm just seeing what is happening here. We're setting a seed so that the same number will come, so that you can check. You can check with your friends when you run it. If you set the seed so that you can check the numbers with each other, right? So the first thing this command is doing is it is doing a NumPy. By the way, of course, NumPy is different from PyTorch. Okay, PyTorch has more concepts. In this slides, you can understand this thing from NumPy itself, because NumPy also has matrices and so on. So np.random.rand will create a random matrix of size 4 cross 6. So this is what this X matrix is. Okay, this 4, 6 will look like this. And then we're getting an A matrix 6, 12, which means it will look like this. I have just shown you the shape, right? So approximately it looks like this. This side is 12, this is 6, so this is longer. Similarly, you can create a B matrix, which is random 12 cross 6, which means it will look vertically like this. If you have 12 cross 6, it will be 12 this side and then 6 this side. Okay. Now, if you want to do matrix multiplication in NumPy, you will do x equal to x at a. Right? This is the syntax for matrix multiplication. This is the very first step you want to do here. So basically, A and B are the matrices, are the weights inside the block. So we are just creating random values to demonstrate in this example. Okay. Now, cutting, right? Matrix is there, but how to cut it? So the commands for that is this. Okay. A 0:2, this will cut along rows. And this is the syntax to cut along columns. So basically like this, you want to do a cut like this, or you want to do a cut like this. So this is the thing. So what I will suggest you to do is, if you want to do, you can do it now, or you can do it after the session. Run this command and see the shape, right? See that, when you take the A matrix, which is 6 cross 12, you run this command, and whatever comes, the matrix will get printed out, and you can see the shape, whether it is 6 cross 6 or whether it is 3 cross 12. So you run the command and you get the intuition. Okay. So this is a demonstration just to give you an idea. If some people are following along, I can just give you 10 seconds so that you can copy this command. I will just drink water. Just take 10-15 seconds. You can try to copy paste this. Okay. So these are the commands to split it horizontally and vertically. So now the question is, I cannot split my x, a, and b, everything horizontally or vertically, right? I can't do that, because what I want for the next stage is x into a. So when you split the matrix also, you have to take care of how you split it. Otherwise, the computation will not make sense. Okay. Like, m cross n cross k, the dimension has to match, right? If it doesn't match, that matrix multiplication itself is not valid. So I cannot say that I will arbitrarily cut everything vertically, because then there will be no synchronization and you will not be able to do the matrix multiplication. Okay. So let's take one simple example where we are saying we'll split x vertically and we'll split a horizontally. Okay. So that means what we are saying is the input, x is the input that comes, right? So we're going to split it up in tensor parallelism. If you're on this, I have 4 GPUs. Actually, this example is showing only 2 GPUs, right? You can take the 2 case because it's easier to understand. When you have 4 GPUs, means you will cut like this 4 times. There will be 3 lines or 3 lines like this. That's how you split vertical columns of your matrix. Now, when we say we're splitting x vertically, which means we will split the x like this and give us different inputs for different GPUs. So for different GPUs, you simply give different inputs. That's okay, right? Then what happens with A matrix is each GPU will again do the cut and only keep one slice, right? And if we are saying we are doing horizontal cut here, which means each GPU will have that slice, that layer, instead of the full matrix. That's how we are saving the space actually, right? If the full thing was 25 GB and we don't have space on the RAM on that one GPU, if we only store one vertical slice, we will have only 1/4 or 1/8 of that full size that we can store. Okay. And the reason for cutting like this is so that you can do the matrix multiplication that we have to do, which is x into a, and it still makes sense. Okay. So basically in a live hands-on thing, if you want to try it, this is what I want you to try. If you do x at a, you will get some results, right? And the split, we are doing the thing that I just said, horizontally and vertically, and then you can check that this value is actually matching this value. So basically the output of the multiplication should be the same before doing this parallelism and after doing the parallelism, right? You cannot change the value has to be the same. But this cut, you can get an hands-on feel that whether that is correct. So what will happen is, if you cut it like this, the way I've shown here, this one vertically and this one horizontally, you can compute x1 at a1 separately on one GPU, x2 at a2 separately on another GPU, and then you can add them. And this add is like the reduce we saw earlier of gradients, right? Where each number will get added up, and then that number, that matrix finally will match exactly the matrix that you would have got if you didn't do any cuts, right? So you can run this and check and ensure that this is correct, this matches, right? So this works. Basically, this works. Doing this kind of split is enough for you to do XA, right? But we have more steps, right? We have more things, like we have to do the next one, Jelu, and then you have to do X into B and so on, right? So for a moment, forget Jelu and just think that I'll go to XP, right? So you want to follow the computation. So if you think what you've done so far is you have computed Y1, which is basically X1 A1 and X2 A2, which is what I'm saying like this, right? So each GPU has this portion separately. And you have not merged it yet because you want to finish the computation, right? We have more layers, so you have to do everything and then we can merge. So to do this, how do we cut B? That's the question, right? Like here we didn't cut B yet. We only cut these two, but you have to cut B also so that that thing matches, right? The shape matches and the sum matches. So that's the, again, I'm showing the answer here in the interest of time. You can try these commands later. So what will happen is you don't actually have to cut B at all. If we cut A the way I've shown horizontally, then B can remain as it is, so that you can do the matrix multiplication. The shape will all match up, and the same addition you can do in the very end, and the final number will match up. So you can try it and you can see it for yourself that this, what I'm saying, is correct. Okay. So now this is what I showed you how to do the cut with A and B. But there is a problem, and the problem is there is a GELU in the middle, right? And we never looked at it, we skipped it right now. So the problem with GELU is actually, if you see the underlying function, right? GELU is used in neural networks, it's a activation function. It is actually, by definition, it is non-linear. Okay, so this is an approximate formula for GELU. And if you see here, it's actually like you have these things, you have 1 plus tan h, you have the x cube and all these things. Okay, so what this means is this linearity, this linear principle is not there. That is by definition, by the way, right? The point of GELU is to introduce this kind of non-linearity so that your neural network can learn some more unrepresentable things. Okay, but if you do this kind of split, what will happen is gx plus gy will not be equal to g of x plus y. This is linearity. This linearity will be gone because the formula is like this, right? You have x cube and you have tan h and all, so it will not work. Which means I cannot do the gx plus y. I cannot basically do gx and gy separately and then add it up like I was trying to do here. Before the GELU function runs itself, I have to synchronize the input. So I cannot basically, what I'm saying is I cannot split up GELU in a convenient way. Before GELU happens, I need to synchronize on all GPUs so that this I can do that x plus y, then apply the GELU. Okay, so now instead of doing that, right, I started with this kind of cut, right? Instead of doing that, you can flip and you can do a different kind of cut. There are many combinations, but I'm showing you the correct combination. In this combination, you don't split x at all. You split the A matrix vertically and the B horizontally. Okay, and basically I've given the commands here. You can run the commands and you can confirm. The final answer will be exactly the same, right? Because the shape and all we have kept. But why are we doing this, right? The reason for doing this is so that we don't have to do that extra synchronization before the GELU. So the way of, if you cut it like this, what happens to y, which is the input to GELU, right? Y, which is after this point, before this point, this XA output. The way if we cut it like this, if we cut it in this different way, what happens is the matrices, the y1, y2 matrices, each element is fully ready. So then basically you can run GELU for this index and that will not disturb, the final answer will not be disturbed. This is because earlier we were actually getting the matrix in a different way. Y1 and Y2 were on 2 GPUs. Now, and they were actually, the actual element for the 0th one would be the sum of the 2 elements, right? Which is not even being represented. So I'm showing you all this. I understand it may be very complex the first time you're seeing this, but the thing to do all this is what are we doing here? We are doing minimum number of splits. Not, they all cannot be vertical. They have to be different things, but you want to ensure that the computation is correct, and you want to minimize the number of this synchronization, right? So the way now we have done this thing is we have actually introduced 2 synchronizations. Basically, this is the full summary. Even after doing everything, actually you basically do one synchronization, which is at the very end, but that's just for the forward pass, right? For the backward pass, there will be another synchronization, and that will be reversed. The order will be reversed. If you did the naive thing, you would have had 2 synchronizations. So you would have had 2 all reduce, one like before the y, so before this portion, and one after, right? Because you change the cut, the way you're doing the cut, there's only one now, which happens at the very end before drop. Okay, so that's the idea, that's the kind of intuition, and the same logic you apply to the attention, to other blocks, and finally you basically do all of those things. I mean, again, I gave you a very basic version of this. There are more complicated versions and more papers about how to do the cuts so that you are minimizing the your communication. Now the end result of this is one layer, because you have attention and the MLP block. You totally will have actually four already. So why did 4 come from? In the forward pass there will be 1 year. In the backward pass there will be 1 year, okay? So in the process, totally you will have 4 already. Now you compare this with the DDP, the first algorithm we showed, where in a single training step, actually there was only one all reduce. That was only one all reduce for the gradients. Remember, that happens actually at the end of the backward pass. Here, totally there will be 4 all reduce. So that is the difference between that algorithm and this algorithm. This algorithm is more computationally balanced, but it has at the cost of doing more network operations. So you have to do more of these all reduce, which can also be costly. Okay. Now the problem, like I was just introducing, There is too many all reduces, that is there is any problem. But why is this a problem, right? So the next few slides I want to give you intuition exactly like why is this all reduce that much of a problem. Then that comes actually down to something called nodes. So let's talk about that right now. Okay, so I showed you this diagram earlier, which is one GPU. Okay, so this is one A180 GPU. But like I said, we'll have a data center full of GPUs, hundreds and thousands of GPUs, right? So we have to scale up. So in this one GPU, you like the same diagram, we saw a different version. So this is the core graphics part, right? This is the actual computation part. There are other peripherals, like we said. So there is a peripheral for network interface. There is a peripheral for motherboard interface. There is an interconnect interface. All of this becomes important when you're connecting more than one GPU. See, if you only have one GPU, if you only have one GPU for gaming or so on, you just have this, you don't really care about everything else, right? But in data center, we have hundreds of GPUs, so we care about all of these connections. So I want to give you briefly idea of how that connection works. Okay, so this thing you see on the top, these things here, these are what is known as a PCIe connection. Okay, so this is the side view of the same one, the same chip. It's inside the box, the side view. You have these PCIe connection. So PCIe is a very standard peripheral connection protocol. So it's a hardware and software and everything. Now the graphics card is coming with these 3 ports. Okay, and the point of these ports is to do what is known as a bridge. So I will talk about this carefully. Look at this diagram and try to correlate. Try to correlate this picture with the next picture. This is one card. Okay, this is one GPU, one chip, one card. Here you are seeing actually 8 cards. So this is 1, 2, 3, 4, 5, 6, 7, 8. You're seeing the 8 boxes, right? So you can buy one at a time, or you can buy a full 8 set. Okay, so this box, this full box that you're seeing, this full machine is what is known as an NVIDIA DGX. So it's basically they're selling you 8 cards and other things in one package, right? So you're buying one full set. So this is what is known as a node. Okay, so you have one GPU in the previous diagram. Here we have a node, and a node usually has 8 GPUs. That's the standard thing, right? You have 8 GPUs in one node. Now further look at the PCIe connect, right? So these two cards, these 2 chips, the PCIe interface I showed you here, this is being connected pairwise with the small square chip. Okay, and you're seeing these 2 connected, these 2 connected, these 2 connected, these 2 connected. So these are what is known as NV bridge. So maybe there's a diagram here which shows this is the logical diagram what I'm talking about. You have 8 GPUs. So this blue boxes are the GPUs. Okay, you have 8 GPUs. Two of them are being connected to the NVLink bridge. Okay, so this is something new that is being added. So this NVLink is an NVIDIA protocol to basically make communication faster. So why are we doing this? We want faster communication. Okay, now every GPU also has a PCI connection to CPU, because obviously otherwise you cannot even do the basic computation. Whatever we run the program, it has to go from CPU to GPU. So all that will go normally via these links. Okay, so when you load, and of course your CPU, this PCI switch will connect to your CPU memory also. So if you download model weights that will be in your CPU RAM, then you will load them into your GPU. So then that will get loaded via the CPU, via this PCI switch, via this orange lane into the GPU. Okay, that's a normal process. So normally you will think for this copying and all, if let's say I want to copy some data from GPU 1 to GPU 2, normally it has to go through this orange path, right? It has to go from GPU to CPU, and then again from GPU back to GPU, and there is some bandwidth for these lines, and there is some software, and there is packets and all those things. Okay, so that's the normal protocol that is existing for a long time. That's how your normal computer works. Okay, but NVIDIA is saying that is not fast enough. So we are giving you new hardware, new links. This is a bridge which will directly connect to these 2 GPUs. So if I do some operation like sending some data, copying some data from this GPU to this GPU or this GPU, it can use this link directly, and that will be much faster. So that will have a separate software, separate code for it, and it will have separate hardware. So it is actually a hardware link. So it's like a separate link, and it is meant only for this purpose, right? If you go via this thing, you have traffic, you have all the GPU communicating, you have all those things. Via this, if you go, it's an instant connection, right? It's a direct connection. You can push more data, you can copy large amount of data immediately, instantly. So that's the idea of an NVLink bridge. Okay, now like the same DGX node I showed you, this actually has those 8 things inside. I want to show this is all from YouTube. If you go search, you can get the nice animation, even NVIDIA's official website. But I want to show you some more components here so that you understand how these things work, right? So inside the DGX base box motherboard, there are 8 A100s. So this is the same chip. You see the chip. I hope you're able to recognize the chip now, right? So this is that A100 chip with the HBM modules, that the small squares, and this is one A100, and there are 8 of them, right? So there are 8 of them connected onto this motherboard. Okay. Now, this is a newer technology. I showed you NV Bridge. Now there's a newer technology called NV Switch. Okay, and that is basically some more hardware on the motherboard. So you see here it's actually attached. So the other things are there in the background. It's there on the hardware, and it uses a proprietary technology called NVLink. So this is NVIDIA's custom proprietary protocol for very, very fast transfer. So you're seeing the number, right? 4.8 terabit per second. So it's much, much faster than the PCIe link. Okay, and it has 6 of these switches on that one board. So this thing, it has actually 6 of those things maybe attached here. For these 8 guys, there is 6 of these NV switches. Okay, and also you finally have your networking card, which is in this case Mellanox. There are other brands and so on. So this is like the same like an Ethernet port that you have in your laptop or your Wi-Fi connection. Think of it like this. This is actually networking across multiple machines. So this is again very fast, because this is 200 GB per second. But you also have 8 of these, right? You have 8 of these NIC. So these are known as NICs, network interface cards. So you have 8 of these on that same box. So in that box you have 8 GPUs, 6 of these switches, 8 of these cards. So you're packing a lot of hardware, right? The more hardware you have, the more speed you can get. Okay, so now this is the new architecture of that DGX. You saw the earlier one with the bridge. Now I want to show you the new one with the NVLink switch and the NIC and so on. Okay, so look at this carefully, you'll be able to understand. So we have 8 GPUs. Okay, these are the boxes here. We have 8 GPUs all in one node. So the whole thing is one node. And now we have the NV switches. So in this actual diagram, they only shown 4. I told you there are 6. Actually, there are 6, but in this diagram they've shown 4. Now the way the hardware works is there is a hardware link between each GPU and each switch. That's the idea. That's the way it is. Okay. So there is an hardware link. There's an actual hardware line in the motherboard between each of these GPUs and each of these switches. That's basically a very fast network for communicating between these GPUs. Okay. So now, unlike the previous case where only GPU 1 and 2 could talk and 3 and 4 could talk. So if I go back to the diagram, you will see that there is a problem here that 2 and 3 cannot talk, right? 2 and 3 cannot talk. They have to go via this, which means it will be slow again. But with this approach, you can see any 2 guys can talk to each other via this full network. And how they will do is they will use all the switches. So basically, it's not that when 1 and 2 have to talk to, they can go like this, but they can also go like this, right? They can also go like this. They do all that in parallel. So the underlying protocol will split the data, will split the packets, and it will use all those channels. And basically, it will really increase your throughput. Right? Earlier, it would have to go via this, which has some network bandwidth and it has some limitations. It has to go like this. There are software limitations. Now it can just quickly talk to each other very fast. Okay, and of course, all these 8 GPUs on one node, so they can talk via these switches. But if you have to talk to another node, let's say there are 16 GPUs, right? Then you cannot do this. This is only for these 8 GPUs. If you want to, if the 8th GPU has to talk to the 9th GPU, which is on the next node, next machine, it has to go via the network card. So that's where for this GPU, there is a dedicated network card. It will go via this. After it goes to network card, it will go to the data center networking backbone, right? Which is a normal existing one that you might be aware from your networking course and so on. It will go to switches and routers, and there are racks and there is top of rack router and all those things will happen. So basically, you will go via this network switch, you will go to the switch and then go to the other node, and on that node again you will go via this. Okay. So the reason for calling out this, why I am showing you all this, right? I am showing you all this because within 8 GPUs, all reduce is very fast. The all reduce operation we have seen now twice. It is used in DDP also and TP also. Pipeline parallelism didn't use, by the way. Pipeline parallelism only used send receive, right? It doesn't have all reduce. The other 2 protocols have all reduce. All reduce is very fast within one node. Within the 8 GPUs, all guys can talk to each other very fast. Actually, they have hardware mechanisms to do things like addition in network. So when this guy sends 5 and this guy sends 5, it will get added up into 10 and it can get broadcasted to everybody, for example, right? So the communication and computation gets kind of embedded. So all this is to improve speed. So the limitation, of course, the limitation is within 8 GPUs, it's fantastic, right? You can do all these excellent things. But the moment you want to go to 16 GPUs, your all reduce performance will really collapse because it has to go via the network card and then it will go back to normal. Okay, so you will reduce, your speed will be very low. So what to do, right? So I am giving you the problem. So actually you can compare. We have shown 3 techniques, and let's compare them. Take a revision. DDP is very easy to implement, and it does not. Only problem is this is the pros, right, and this is the cons. So the cons is you can't use it if the model is too big, right, and it doesn't scale. Pipeline parallelism is very simple in networking point of view, right? It does a send and receive, but its problem is it has too much empty space, right? The bubbles are too bad. You can't that's really bad. TP is best in terms of computation balance, but it is impossible. It's very costly over multiple nodes. Okay, and of course we have to use hundreds of GPUs, right? We cannot do just with 8 GPUs. So the immediate thing that comes to mind. So what can you do? You can actually put together all these three techniques, and that is known as 3D parallelism. So just think about it. We are saying each technique has some advantage and disadvantage. We want to combine and do all the three for different subsets, such that we can maximally use the advantages of each of those protocols. So I have purposefully left this diagram very minimalistic. I want you to think about it. What I'm saying here, each of the small squares, right, is a GPU, and I specifically put in boxes of 8. So you see this box of 8 is one node. So in this story, I have 4 nodes, which means 4 into 8, 32 GPUs. I have 32 GPUs. Okay. Now, because my model is not fitting, I can't do data parallelism. If I do pipeline parallelism, it will be too many bubbles. If I do tensor parallelism, between this, there will be a complete killer. Throughput will go. I cannot do tensor parallelism. So what is the best way, right? I am combining all three techniques. And how is that working? We will first take data parallelism. Okay, so we will say I will take my full data set. I will split it into 2 parts, and the first part will be dealt with this first half, this top half. The second part of the data will be dealt with the bottom half. Okay, and we're going to say we will just apply the DDP technique. So for the moment you forget about like what is happening inside, you imagine somehow what's happening, and end of the day there has to be one all reduce between these two. Correct? That's the first thing we saw in data parallelism. There's one all reduce at the end, and that has to happen between this full set and between this full set. Right? That sort of thing. Within this full set and within this full set. Now you kind of zoom in and you say, okay, you know what? Now within this input, so you can basically forget about these two nodes, just focus on one, and you kind of zoom in and say, let's do pipeline parallelism in a way that the send and the receive will go via this border, right? Because that's the slow part. And we will do tensor parallelism within this portion, within the node. So within the node, all reduce will happen very fast, very good. But we will arrange the stages. So basically, first we will cut it horizontally, and one horizontal stage we'll put inside this. Then within this, we will cut it vertically, and then that will be split between these GPUs. Again, I know that can be very confusing. I just introduced 3 different concepts, and then I'm trying to mix everything. But I'm sure if you just think about this later and come back and look at this slide again, I'm sure it will make sense to you. Idea is we are doing all 3 protocols in a nested manner, so that we are taking the advantage of each protocol at different stages. So like I said, you can do the send receive. So send receive is cheap because it's a point-to-point thing. Okay, so that you can do across the nodes. So it will be slow, yes, but it will only be once and the end of the stage. But all reduce for the tensor parallelism will be 4. There will be 4 of them. But we have designed in such a way that those 4 things will happen within these 8 GPUs, which means they will happen within this set, and which means they will be fast, right? So that's the basic idea of that design. So basically, I just wanted to show you that, based on the impact of your actual hardware, your algorithms, your software will change, right? The fact that 8 GPUs can communicate faster, but apart from that, they don't, then you have to take those kind of hardware constraints in the real world, and then you drive that into your protocol algorithm design, right? So you cannot design algorithm, without thinking about the low level hardware. That's the kind of lesson I wanted to give here. And of course, because a lot of money is involved here, because it's a very large scale thing, these companies are all spending a lot of effort in optimizing and coming with more and more efficient algorithms, like we've seen. So to do this 3D parallelism, actually there is a lot of parameters, right? Where you split, what is the vertical split, what is the horizontal split, how many GPUs. Based on all of this, based on your model size, you come up with a different schedule. So there is software to automatically calculate, the schedule. There is research about how to make that schedule better, and so on, right? So just to give you a taste of the kind of things out there, right? It's not the simple thing that I just showed you. Now there is a separate algorithm here. I'm going to just skip this. It is more complex, but it is alternative approach. Instead of doing the 3D parallelism, what you do is you take the data parallelism and you're doing something different to try to do the phase the same. At the end of the day, the problem is the same. You have limited memory and you have constraints in terms of your network capacity and your compute, and you want to maximally fit within this, right? This is just one more algorithm. I am just showing you this because you can go read about this. There is papers, there is very nice YouTube videos talking about this. I don't have time to cover in full details, but you can go look into this if you're interested. And there is code for this open source. There is a lot of research potential here going on in this entire space. So just to give you an idea of what exists, and there are variants and so on. I will just briefly talk about the challenges in this, right? That the kind of things we have seen. There is a lot of competition also. There's a lot of communication also, because communication, you might know this already. Communication is very slow, right? A GPU will do competition very fast, but if a GPU has done the competition and then it's waiting, right, that's not good. So you want to design your algorithm so that while you are doing communication, some other computation can run on the GPU, right? And similarly, network speeds are very low when you start scaling up, right? When you're connecting thousands of GPUs, all the network time will add up, and that leads to more wastage, and that's bad, and try to fix that, right? And similarly, larger you grow, the more the algorithm will change. These algorithms have showed you, they are good for 8 GPUs, 64 GPUs, 128 GPUs maybe, right? But you go to 1000 GPUs, right? The algorithm I showed you will not, right? You need more complex algorithm. Of course, the basic logic is the same that I've shown. You have more variants, and I will show you in the next few slides. We are almost towards the end. I just have a few slides talking about,
we have 5 more minutes, sir.
Yeah, sure. I will just take 5 more minutes to just kind of finish up and give you just an idea of some other things that exist out there, right? So you saw this simple pipeline parallelism I showed you, right? This is a simple thing where you're doing this thing one after the other. Now there is, I'll show you one variant, and you might think that, oh, okay, you know what, I could also come up with this, right? So instead of doing, like 1, 2, 3 like this, you're actually, mixing your forward and backward. So you're switching a reverse schedule. You're not, if you can compare these two diagrams. Here you did 8 micromatches forward, and then you started the backward, right? Instead, you're actually mixing up the backward and forward. Now you will ask, why is that, right? And that is because you actually have lesser bubbles. So there are papers, I think I have a slide here, which actually do this, computation of bubble ratio. They're measuring, what is the ratio, what is the wastage, and they're then coming up with better ratios. So they're coming up with new algorithms which reduces that, white space. So that's research. And there is one more example here, which is also very, very interesting when you realize. It's a paper called Chimera, where they actually run 2 pipelines, but in reverse direction. So what I mean is, the pipeline starts from device 0 to 4. At the same time, another pipeline is running from device 4 to 0 in parallel. So if you think about this, you have this thing going, you have another thing going like this, right? It's a very, very simple idea actually. And then there's a full paper about, how they've done this and how they actually managed to save more space. Right? So this is an example of research. Ideas are very simple because the concept is simple, but of course, implementing it and figuring it out at the right time, right? A lot of challenges there. Now, just 2-3 minutes, I'll just talk about the higher level thing. Right? I've talked about the algorithms, right? But they run in real world systems, and those real world systems are like large data centers. So like I said, you have racks and you have switches and routers on top of the racks, and they connect to backbone and so on, right? So this is a paper. If you're interested, I'm just giving you some links here for things you can look up. So this is a paper from our company. This is our internal data center design. So this is in this conference, which goes into detail about, how it's connected and why they took the decision and what are the advantages and disadvantages and what worked for, right? This is more about the data center design, but this is like a larger problem. Now in this paper itself, actually they talk about this, where how, as the network size, as the number of GPUs increases, your amount of time it takes and the amount of time that is spent in the communication, actually, you can see how it goes down. So what this graph is showing is, when you have 48 GPUs, you're pretty much using the full compute of all 48 GPUs, okay? But when the moment you come to like this large number, like 1500 GPUs, actually the total compute, if you see at the end of the thing, with the best protocol that we have, you will see actually we are only doing 75% compute utilization. Means 25% time, or there is computation which is not even it's being wasted. And why is it wasted? Because of all this network overhead, right? There are so many GPUs and they all have to talk to each other. The best protocol, even with all the research, even the latest research, there is still so much idle time for the GPU. And this is like, I'm just showing you the pending future problems, right? These are the problems that is there, that enterprises are facing, how to reduce this number, because 25% of thousands of GPUs is a big number, right? It's a lot of wastage. There's another challenge here, right? In traditional computing, cloud computing, there is a nice graph of traffic in and out. So there's a very generic graph because different people are connecting at different times. It's night in India, it's morning somewhere else. So you have these different patterns and they all kind of merge, right? So you have this nice graph. But in network, in this thing that we saw today, in the algorithms we saw today, when all reduce happens, all the GPUs will do all reduce. So actually what happens is the network throughput spikes in a very crazy way at a very narrow points of time. So then for another 2 minutes, there may be no activity in the network because all the guys are computing, right? And then when they're done with the computation, they will do it all reduce, and every GPU is sending a packet out. and all the packets, there's at that time there's so much traffic. So if you see here 400 Gbps, you have the huge spike of traffic, but just for a small window, and then again it goes to zero, and then again it comes and goes. So this is kind of a different pattern. This was not there before, right? This is a new pattern with GPUs, and that means there is more problems with the network switches and everything. This was not how it handled. We have more congestion. So these are kind of open problems, right? That, oh, we have to solve these things. They were not there before. Now they are there because this distributed trading is like this. Very interestingly, there is this thing of papers talk about the data center temperature and impact of temperature. Okay, so there's a lot of variation, and GPUs are run very hot. They have high electricity consumption, so they also get like throttled. If the temperature goes up, they start throttling. And like you saw in this algorithm, one GPU throttling will actually pull down all the GPUs because they'll all have to wait for the result of this GPU, right? So that's why there is a huge amount of work going into cooling and how you're managing your data center cooling. So this very funny graph I wanted to just leave off this diagram. It's from a paper. It's from a serious paper. It's a very good conference. If you're not yet, it's a top level paper. It's from Tencent company. One of the things contributions they're saying in the paper. Now, this is not a joke, right? I mean, the paper is talking about very complicated things, but in the middle, it also has this diagram, and they're saying, the contribution. One of the contribution of the paper is the traditional airflow in the data center was like this, horizontal. Like the fan, you kept the fan, and it was like this, and that didn't lead to good cooling, right? And now they've kept the fans like this. They've changed the fan order, and that leads to more efficient cooling. And the joke is not just that. It's like if you see the range of temperature, it's 22.01 degree. 22 degrees is already very cool, right? It's a cool. 22 degrees is cool. 22.01 to 22.94. It's not even 23, right? So it's within 1 degree centigrade. And they're saying that, after this optimization, they have brought that, variation of temperature from 1 degrees to like 0.1 degree, right? You see here it's like 0.1 to 1.2. And apparently that's that big of a difference, right? That cooling, that difference, that one managing the temperature within 1 degree was so important that they saved so much dollars and so much money, because that impacted the whole distributed trade. So I just wanted to leave with this, that when you have this high level of GPUs, you have these kind of like unexpected problems. We have seen the algorithms today, so I'll just give this recap. This thing, we have seen a few common algorithms that are being used. They're more complicated algorithms, but the idea is to manage a large fleet of GPUs and training and managing training at that scale. Thank you. Yeah, this is what I had. We can close the call.
Okay. We'll go for the Slido quiz, and then we'll have the Q&A answers. Sir.
Sure.
Okay. I have pasted a Slido link quiz in the chat box. Request the participants to join the Slido quiz. My screen is visible?
Yeah.
Okay. Participants, I have pasted the Slido quiz in the chat box. For the YouTube participants, I have also pasted the quiz there. You can use the link and join the Slido quiz. Hope past 2 days you have practice of the Slido quiz, how to attend. It is a multiple choice question. We'll have 20 seconds for the each question. Total number of questions will be 5. At the end of the quiz, we'll have the leaderboard. I request the participants also to join their Slido quiz using their name and iPhone college name, so that we can identify them. We'll wait till it touches 400. So. Okay. We'll start the Slido quiz. Here is the first question. You have 20 seconds to answer the question. Okay. It is a mixed response. We'll see the right answer. Okay. Sir, do you want to explain anything? Because most of them got 21%
So
of the one.
yeah, so one forward pass usually only gives you one token, right? Like if I say, if you ask a question and it says the answer is, so you need one forward pass for each token. So there will be a forward pass, answer will be forward pass, and that happens automatically. You ask a question, you will get a full response, like 300 words, and that's the end. That's why we're seeing there are many forward passes that happen, and you get all of that, all of the results too.
Thank you, sir. We'll move to the next question. Okay, 70% of them answered B. Let's see. Okay, most of you got the right answer. We move to the third question. Okay, 79% of them got chose B. Okay, again, B is the answer. Move for the fourth question. Okay, the answer is A. And the last and final question of this Slido quiz. Okay, let's see the right answer. Okay. Before revealing the leaderboard, I request participants to come to the Zoom screen. We'll have the leaderboard. Request all participants to come to the Zoom screen. So we'll have the leaderboard revealed. Okay. Okay. John got all 5 answers in 47 seconds. Prince got in 50 seconds. So congrats to the all participants. We'll go to the Q&A. The chat box is open now. You can type your questions there. Or you can raise your hand. We can unmute you.
I think, Kishore, in the meantime, you can read the question which we have already received from the
Yes,
participants.
yes. I'm coming to that. Just a minute, sir. So this is the question we got. Sir, I have a doubt regarding the optimizer slide, like an rewind loss surface momentum improves coverage space speed. Does it always guarantee faster coverage, or can it sometimes make it training unstable?
Right. So actually, a lot of research has gone into optimizers. So the ones we use are commonly already proven to be very good in all aspects, right? So they don't make it unstable. So the research is already gone. Of course, it's also an open area. So I mentioned this Adam W. These are very common optimizers we use today, but they're actually newer research. Like I think last year there's a new optimizer called Muon, and that makes it even faster, right?
I
With
should-
lesser resources. So there is a lot of research. It will be stable because it's others have already done the work for you.
I request the participants to type your question. Okay, Vishnu Priya, you can unmute now. Vishnu Priya. Okay, any other questions? You can please type or raise your hand. I can unmute you. Or you can type it in chat box. Okay, Surya Prabha from RIT, Ramco, you can unmute.
I think if you are not able to unmute, please put the question on the chat box.
Hello. Hello.
Yeah,
Yes,
go
I
ahead.
can hear you. You muted again.
Hello.
Yes, you are unmuted. You can ask now.
Sir, tell me about optimization bytes. Hello.
Yes, sir.
Sir, clarify me about the optimization bytes.
Optimization?
Bytes. Yes. Clarify me.
Okay. So the
Okay.
question is about what is the optimizer bytes, right? So the thing is, each optimizer is a different algorithm, right? So the one I showed you, which is into 3, which is actually the common Adam W optimizer. So that optimizer has something called momentum and variance. So basically what it's doing is, for every parameter, it is tracking the history of how the parameter is changing, right? That's where I showed you that instead of having this sharp turns and gradient descent, you can do an average. So you basically know that it's going like in this direction, and you can bias it in that direction, right? So that's why every parameter, it will actually have 2 extra fields, and that makes it 2 plus 1 3, and each parameter is in 32 bits, so that's bytes, 4 bytes, right? So that makes it like into 3 of whatever is your model size. So if your model size is 25 GB, that's because that means that it's 8 billion parameters. So 8 billion parameters into 3, you can get approximately the optimizer state size, and the state is created and kept during the entire training process. So once training starts, it will create the state. First it will be 0, it will not be there. Then after the first step onwards, it has to have that state continuously in memory, because it has to keep track every time, every step, how the gradient is changing, what is the momentum, what is the variance, and so on. Now other optimizers may do something different, right? That's where that research is. You may not need in 12 bytes, you can do it in lesser number of size, or you do mixed precision or those kind of things. So that's where the space is good.
Okay, thank you, sir. The next question is, sir, why does the optimizer require additional memory apart from the model parameter? What exactly is stored in optimizer memory?
Correct. So there are 3 fields, like I said: momentum, variance, and the weights of the model itself. Now it's a good question of why there are 2 copies. I am also not fully aware. I can check this up. You can also search, but I'm not aware of the top of my head. There is a difference, right? It's not the same. There is a reason it has separate copy. It's not that there is a waste duplicate copy. There is a reason for having separate copy. I don't know the reason myself, actually. But yes, it's a good question, because that 8 plus 4, right? That extra 4 is, you feel it's duplicated, but actually it is required.
Yeah. I think there's no more questions, sir. Thank you for the insightful session. Now I request Mr. S. Krishna Kumar, PALS champion, to give the closing remarks.
Yeah, there is one more question from student. There is one somebody holding his hand.
Okay, he can't
Student.
unmute. There's a mic problem in his. I
Oh,
think
it's okay.
there's some more some
I
question.
think
If
you
GPU
can
is
send your
limited,
questions by email,
okay.
which will pass on to Mr. Chandra Govindrajan, and he can respond later. Okay. So good
There's
evening,
one
guys.
last question. Can I go? Can we go, sir?
Yeah.
If GPU is limited, what are some practical techniques to reduce memory usage during training?
Right. So the simplest thing you can do is this quantization, right? Quantization and sparsity. Now this is very practical. when you have like you're trying to do models on your own, right? You have a consumer grade GPU, you have a gaming GPU, and a lot of techniques, and this is a continuous research, right? I think a good place to go look at stuff is Unsloth. So there is a company called unsloth.ai. So they do a lot of work around optimizing, again, with quantization. So by quantization, what I mean is, instead of doing 16 bits to store one field, one parameter, they will use 8 bits or 4 bits, or there are papers that say 2 bits and 1 bit. Now the lesser you go, the more your model become approximate, right? So you will be running it, but it might give bad results. So one is, you have to choose a smaller model. So you definitely can't take the biggest model, but even for a smaller model, the more you quantize, the more you will get impacted. So the other project you want to look into this is llama.cpp, right? Or also olama. So I think if you're interested in the programming or the underlying aspect, go to llama.cpp. So this is basically a way to run this quantized model on your local laptop, and that code is all open source. It's all like C++ kind of thing, and they are using maximum whatever they can do on a single hardware. And you can even run very big models like GLM, like the latest model, which is actually a very big model, especially if you have a Mac, right? I mean, even it works on any laptop actually, or even works in a normal enterprise server. If you have any server like just lying around, if you have something in your college which is like a good computation unit with no GPUs, you can still use llama.cpp to run this quantized model. It can give you decent results, right? You can try it. Mileage will vary, right? You will not get the best results, but that's the way to go.
I think this is the last question. When Dinesh has raised his hand.
Dinesh, you can unmute if you want. I have requested you to unmute. Over to you, SKK sir.
Okay. So probably you can send all the questions by email. Now I would like to thank Mr. Chandar Govindarajan, who has given an excellent presentation of distributed training. And I mean, even though I am not an IT person, a specialist, I am not an IT specialist, but still I could make out some portion of what he has talked about. I am sure that others with experience and knowledge and studying in IT groups and CSC and all that will definitely would have found this lecture quite useful. And this recording will be available from PALS to the students and the faculty later on. And I would like to thank Mr. Chandra Govindrajan, who has given an excellent presentation. And earlier, the first session on Aishwarya Chakrabarti and Priyanka Nayak on PyTorch basics and advanced PyTorch. Then Kavya Govindrajan on inference systems. Excellent. In fact, I would like to thank IBM and Mr. Kamal Das for having organized this kind of training program for the faculty and students of our participating institution. I'm very happy about the whole thing which went on the last 3 days, third, fifth, and today. I'm very happy about it. Thank you very much, Mr. Chandar,
Thank
and
you.
others
Thank you
who
for
have done
PALS for
this.
organizing this. Yes.
Thank you very much. Thank you very much, PMO, and also the students and faculty who have attended this program in large numbers. Thanks a lot.
Thank you.
Thank you, Chandra sir, for the excellent session.
Thank you. Have a nice day.
Thank you, sir.
Yeah, thanks a lot. We'll close the meeting.
Okay, sure, sir. Thank you.
Good job, Kishore.
Thank you,
for the
madam.
coordination.
I request all the participants to mark your feedback for the session 3, all the sessions. I have posted the link in also the WhatsApp group. You can find the link there. You'll get the certificate by next week.